am looking forward to our afternoon lineup, which will be introduced by my talented and glamorous co-host, Leo Llanos. Leo is a creative director, designer, and photographer. He has collaborated with Amazon, Twitch, GLAAD, and the Grammys Recording Academy. His work has been featured in Entertainment Weekly, BuzzFeed, Billboard, and Attitude Magazine. He is currently the design manager for Foundation for the Future, where his creative work is helping to brand its mission to accelerate space access for everyone. Leo, you have the microphone.
Thank you so much, Lee. Yes, thank you so much. And by the way, your daughter looked amazing. She was so cute. Again, thank you so much, Lee, and thank you to everyone for joining us here on Conversations for the Future. Our next speaker is Dallas Bienhoff. Mr. Bienhoff is the founder and space architect of CisLunar Space Development Company. CisLunar Space Development Company is a space transportation and logistics company defining a reusable CisLunar transportation architecture for satellites, lunar cargo, and human lunar development missions. Their vision is to provide commercial transportation from low Earth orbit to the moon's surface and all points in between. Welcome, Dallas, and thank you for being with us today. The screen is yours.
Thank you, Leo, for the introduction, and thank you, Michael Lane, for asking me to participate. This has been an interesting morning. Before I start, I'd like to share some anecdotes to link this morning's talks with what I'm about to talk about. So I first learned about space-based solar power in 1976, I believe it was, from a Popular Science article. I was working at Rocketdyne at the time, and I took that article to my manager and said, maybe Rocketdyne should get into the space-based energy market, because Rocketdyne was proposing to build the solar power satellites for space station at the time, Space Station Freedom. That went nowhere. Rocketdyne had its rocket engines and its space station project. So that was my first entree. A few years later, I was at the Aerospace Corporation after Boeing and Rockwell completed their studies for NASA and the Energy Department on space-based solar power satellites. And I did a critique for aerospace on the transportation architecture, i.e. what it took to launch and create these humongous Manhattan-sized solar arrays in space, build them in low Earth orbit and take them out to GEO. There were launch vehicles proposed that had over 4 times the lift capacity of the super heavy Starship, 454 tons to orbit. There were space tugs to take 1,200 tons from low Earth orbit to GEO. These were electric powered. And there were people transports that took 70 people out to GEO and rotated them back and forth. This was a massive undertaking. Still exciting. And then I got to work with Coyote, as he mentioned, on this 2007 study while I was at Boeing, and supported that activity. Saw it go nowhere again. They got their cease and desist order. And a few years later, with John Mankins, I was at the UAE for a space-based solar power conference. Went back to Boeing. We also heard about reaction engines, Sabre engine, this space Sabre, synergistic air-breathing rocket engine for a single stage to orbit system. I took that idea and the concept again of space solar power alpha to Boeing and said, maybe we should investigate launch vehicles to build this, should it be funded. That kind of went nowhere as well. On the opposite side of that, Boeing has since invested in reaction engines for the Sabre engine. And I've read that they are looking at point-to-point transport as well as hypersonic vehicles. So not all is lost, not as fast as we would like to see things happen, but things do move slowly in large corporations and in bureaucracy. So that's my link. And then to get to where we are today on space transportation, I was the Boeing project manager for how to implement the vision for space exploration in 2004. And we put together an architecture that used different transportation modes for launch, for in space, and for getting down to the moon. Rockets to get to orbit, separate that from getting from orbit, Earth orbit, to the moon's vicinity, and separate that mode of transport from the moon's vicinity down to the surface. That, coupled with a question from a colleague and friend as to what is a common impedance architecture for getting from Earth to the moon. Common impedance is an electrical term. I prefer resistance. You know, how do you get the same mass you can launch onto the moon's surface? So again, separating out that payload from launch into a payload for transport into a payload for landing. And at the time, the largest vehicle that we had, largest launch vehicle, could put 25 tons into orbit. So the question to me was, what does it take for a space tug to move 25 tons from Earth orbit to the moon? And what does it take for a lander to put 25 tons to the moon's surface? How big must they be? And so that's the whole story behind what you're about to see on a CisLunar transportation architecture. Leo, you mentioned this, but our vision for CisLunar Space is to provide safe, reliable, available CisLunar transportation for people and cargo. So how do we do that? So we want to commission and operate a reusable transportation architecture to move material, and material encompasses people, cargo, propellant, anything you want to move throughout CisLunar space. And that's not just to the moon, it's to geosynchronous orbit, to geosynchronous transfer, relocating things within space, providing the means to do that. So our initial minimally viable concept takes two system developments: an Earth to orbit refueler, which you see on the left, which is really a payload and return vehicle and payload fairing on top of a launch vehicle. I happen to be showing the New Glenn here. That refueling capability is sized to match a space tug, whether that's propulsive or aero-assisted, i.e. using the atmosphere to come back to low Earth orbit. And that can then be the start of a reusable CisLunar architecture. The only thing in this concept that is not reusable is a second stage of the launch vehicle. Now, this is going to reflect somewhat on SpaceX and Super Heavy, but we'll talk about that at the end. This is the fully deployed architecture. It has a propellant depot in low Earth orbit, a propellant depot at Earth Moon L1, propulsive space tugs to do non-geosynchronous or non-high energy transfers, aero-assisted tugs to service the delivery to geosynchronous orbit to the operational longitude of the satellite, so they can remove their station or circularization propellant from their designs. A large 25-ton space tug, i.e. payload of 25 tons out to Earth Moon L1, and then a 25-ton payload capability moon shuttle from L1 to any point on the moon at any time, not constrained by orbital mechanics or other delays such as we see with the NRHO gateway. Now, these can also move payloads round trip at less than half the mass that we can take one way. We also operate down below station to pick up payloads to bring them to the depot. We refuel the depot, and these depots notionally are water to liquid hydrogen, liquid oxygen production facilities. And with that, we can service most of, or half of LEO, geosynchronous orbit and other geosynchronous equatorial orbit and other geosynchronous orbits, and any point on the moon. So what can we do with this architecture? We can do delivery missions. We can retrieve payloads from orbit and bring them back to low Earth orbit. We can do round trip missions, i.e. we can carry sensors to any place in Earth orbit or out to the moon. We can carry people round trip in our personnel module. And we can do disposal missions. We can go with a toolkit on front of our tugs, we can go grab large space objects that are no longer functioning and deorbit them to improve our sustainability of the LEO environment. But we can do up to 25-degree plane changes and back if we don't change altitude, i.e. in the same orbit. We can go 25 degrees away and come back. Plane changes in Earth orbit are expensive energy-wise. Our tugs can do that. And as we gain altitude, we can do less. We can put up to 210 tons per year per tug onto a geosynchronous transfer orbit. Today's satellite designs, without changing them, we can change the way we do business in space and get 210 tons per year to GTO per tug. That's once every 2 weeks. With our aero-assisted tug, we can put up to 104 tons to GEO per year per tug. Now, this assumes we're operating every other week to GEO and every week to GTO. We also would have a 140-ton propellant plus 140-ton water depot in low Earth orbit to support these missions, to refuel our stages between missions. We could transport 156 people per year per tug in our personnel module, whether that's back and forth or around in low Earth orbit, over to space station, if we have a space station operating point, or just loitering in low Earth orbit. We could push up to 300 tons to Earth Moon L1 per year per tug. People, cargo, propellant, 72 people per year per tug to Earth Moon L1. Bringing in the Moon Shuttle and a depot at Earth Moon L1, we could put that same 300 tons or 72 people down on the moon's surface per year per Moon Shuttle. An architecture has multiple copies, so we have at least 2 in orbit of every item and another on the ground for spare, except for the depots. We'd have a ground spare, but wouldn't have multiple depots for servicing the moon or geosynchronous orbit. So this architecture can service the moon, and it can service geosynchronous orbit, GTO, geotransfer orbit, and any other orbit that's within 25 degrees or less of the depot location, which in our reference is 28.5 degrees due east out of Kennedy Space Center. So operationally or graphically, this might look like this, with the size of the red lines being the flow, the amount of flow that goes to each destination. And this is our reference architecture. So we're basically servicing the moon via Earth Moon L1 and geosynchronous equatorial orbit via our 28.5 degree propellant depot. Now there's a station out here that's getting serviced. There's other geosynchronous orbits and GPS orbits, global positioning satellite orbits, that can be serviced, and we can reach those from our depot. For our non-aero assisted tug, we have a inverse parabola that can be serviced. For our geotug, we can service all the way out to about 56 degrees in geosynchronous orbit from our 20.5 degree tug. In the Artemis program, we could also have a depot at NRHO and help NASA and their Human Landing System program get down to the moon. We had serious discussions with 2 of the proposers for HLS to put a depot out there and serve as a propellant provider to Dynetics and to Blue Origin. Unfortunately, NASA only selected 1 candidate, and they have an integrated architecture. So we're looking at other ways to move forward. Another idea is a propellant, strategic propellant reserve, and more depots. We can put depots at the space station, and then we can service almost the entire geosynchronous orbit from equatorial up to polar from those two depot locations. We could also have a depot in geosynchronous orbit, whether at non-equatorial, and reach them from Earth Moon L1 with lunar resources should they become available from a third party. And then finally, with solar power satellite, that traffic overwhelms everything that's going on. If we want to build SPS alpha out of lunar resources, there's a huge flow of material from the moon through Earth Moon L1 and then down to geosynchronous equatorial orbit. That would also support our other depots in equatorial orbit. And it reduces the amount of propellant we have to transport out to the Earth Moon L1 from Earth. The key is the cost to produce that lunar propellant and get it to Earth Moon L1. And the price has to be less than what we can get it to the Earth Moon L1 from Earth. But what about super heavy Starship? You know, that's the big competition in this architecture. With super heavy Starship, Elon Musk back in February in a CNBC article said he believes the operational cost for a super heavy is $28 million. Cost, not price. Who knows what the price will be, but that's cost. To put 100 tons on the moon, it takes a total of 13 launches to do that. 1 launch for the cargo, 12 launches to fill the Starship in orbit with propellant to get it to the moon, to NRHO, with enough propellant to get down to the moon and come back up and come back home. If one is taking 0 payload to the moon, the Starship still needs 9 launches of propellant, assuming that propellant is 100 tons, that propellant capacity is 100 tons. So in essence, Starship can get anywhere in the solar system, at least as far out as Mars, for less than $400 million of operational cost, with 100 tons at the endpoint. Even with that capacity, building something like SPS Alpha is going to take thousands of launches to build just one. But this is the promise that's ahead of us if we start now and move forward into totally reusable architectures and stop throwing things away in space, on the way to space, and on the lunar surface. So Michael, thank you. Let's talk.
I want you to use that last line you just said about not throwing anything away. Just repeat that.
Let's stop throwing stuff away in space, on the way to space, and on the moon. You know,
Like,
two of the human landing system concepts left landers on the moon or drop tanks on the moon every time they went.
mm-hmm.
And that was our problem, when I was project manager for Boeing on the vision for space exploration. You know, we left landers on the moon. We only left half of what we used because we reused the cargo one for the crew, or the other way around. So we used them twice, but that's a litter box, not a litter box. We don't have cats, but you know, it's a junkyard of hardware that can be used in the future, maybe. But let's stop doing that. Our CisLunar Space Development Company's basic requirement is 20 years of operational lifetime, 240 operational missions as a goal for our system, which means that the cost of our missions is 90% driven by the operational cost of getting propellant to them.
Yep.
Not the hardware cost.
I think that really needs an exclamation point, right? That this isn't about one and done. It's not about flags and footprints. It's not about political power. It's about building an industrial system and an infrastructure that is reliable, reusable,
Dependable and available.
and that, I mean, that shouldn't be new anymore, right? That shouldn't be new,
Right.
but that's how we've been operating for the last 60 years of space.
We used 20-ton capacity launch vehicles to put 4 tons of operational mass in GEO today. And we throw it all away except for the operational mass in GEO.
Right. And you have organizations like NanoRacks that are reproposing an idea that's been around for 30 years, 40 years.
A wet lab.
Of using reusing the upper stages.
Right.
Like nothing about this is new. What is new is that there's a path forward that there wasn't before.
Right. So one of the things that we discovered when I was working the Space Launch Initiative in the early 2000s, we had a requirement I should say a requirement, we had a study to look at fully reusable launch systems to space station and to service the commercial crew market. And we had a 400 mission lifetime requirement, which was 4 times what the shuttle orbiter was. The biggest issue for making that happen was the amount of tests we had to go through on the ground to certify before we could fly.
Mm-hmm.
A factor of 4. So we had to put the systems through the static test articles through 1,600 flight cycles. We didn't have facilities, we didn't have time, we didn't have the money to even do that, let alone build and fly and operate the system. And the beauty of the space hardware, the space tugs, is their environment that they're exposed to is significantly less than a launch vehicle.
Oh yeah. I mean, you don't have the same shake and bake requirements of every single time you come up and go up and go down.
They go up protected, they stay in orbit. They don't see heavy launch loads or aerodynamic loads every time they fly. The thrust is a lot less. I mean, they're just a lot more benign environment, but they are mostly propellant. 80% of what we need to put in space to put something where we want to in space is propellant.
Right.
That's a rough number.
So let's talk about that, right? So we've got a really great architecture here. We've got a good design. All of the parts enable the next part, and that enables the next part. So all of this is almost a Lego-like system where each piece integrates with the other piece.
Right.
That's awesome.
Integrated. You got to think integration. You got to think, what can we do not only in reducing the cost of acquiring it. Each tug is a learning cycle for the next iteration or the next size up. The LEO tug and the Moon shuttle are almost exactly the same propellant quantity. So they could be the same vehicle,
right?
Except one has an aeroshell on it and one has legs on it for landing. And the GEO tug and the GTO tug are smaller versions. So they're your early version for learning the systems, the cryofluid management, demonstrating that, the cryofluid transfer, the aero braking, all of that. And all of that grows into the next system.
And that is kind of the hard part though, right? Managing the fuels in that ultra harsh environment, maintaining it, moving it from one vehicle to the next vehicle. That's, I won't say it's unknown because some of it's known, but it is really complicated. So talk about why that's such a big deal and why it's so hard.
So I'm gonna rebut what you said about it being hard. It is the probably the most difficult thing to do because we haven't done it in space yet.
Right.
But I don't believe it's as hard as some people would lead us to believe.
Oh, all right. So
We
tell me more about that.
NASA has ground tested cryofluid management devices for LOX hydrogen. They have ground tested cryocoolers for use on things of this scale, both 90K, i.e. liquid oxygen temperature, and 20K, liquid hydrogen temperature. There are excellent insulation materials that can significantly reduce the amount of heat load into the tanks. And so if we're not liquefying a gas, if we're just trying to keep it liquid, we can do that on these tugs.
Okay. Okay.
The depots you see in this picture, they are water to cryo depots. So we take water up,
Right.
easier to ship, easier to handle, easier to transfer. We produce the propellants on orbit and store them. But these depots, that's 500 kilowatts of solar arrays. 5 times what's on space station.
Right. Yep.
To convert about 70 tons a month of water to cryo and to liquefy it, to gases and liquefy it.
We've got just one time for one more question, and I'm curious. There has been a lot of talk about creating an exchange, a commodities exchange
Right.
for on-space assets.
Right.
Has any of that kind of crossed your radar? Would you participate in that sort of thing? And you know, that, because that would set a price for your product, right?
Well, yeah. Also how we do things today kind of sets a price, kind of an upper price. But I had discussions with Daniel Faber of Orbit Fab years ago about commodities with Bruce Callahan.
Cahan, yep, I know. Yep.
Listen to his presentations and others. My point at the time when I talked with Daniel was, how can you sell something that we don't have a place to store or a user for?
Mm-hmm.
You know, but be that as it may, there's this also subject of the strategic propellant reserve.
Yep.
Troy Bruno at ULA has talked about it. He has discussed it on several occasions online and talks about a $25 billion effort for a strategic propellant reserve. With an architecture like this in place, you could have a strategic propellant reserve for less than 1/10 of what Tori's talking about, because you pay for an added capacity, or you pay for an extra location, or you don't develop the moon's ability or the ability to get propellant from the moon to support your strategic propellant reserve. You start from Earth with what you have and you expand its capacity so that you have more than what the architecture needs to service what the Space Force might want.
Right.
Less than 1/10 of the number.
Crazy. Terrific stuff. Dallas, you're going to stick around here. We're going to come back and talk a little bit about current events here in a moment.
I will be around.
Turning it over to you. Thanks a lot, Dallas. Appreciate it.
I will stop sharing.
Thank you so much, Dallas, for that amazing presentation and information on space tugs.
You're welcome, Leo.
Thank you. And for being with us today on Conversations for the Future, of course. To continue the networking benefits for this event, Dallas, if you could please just put your LinkedIn link on the chat or comments so we can continue networking. And for everyone listening, thank you for joining us for this Conversations for the Future powered by Foundation for the Future. Conversations for the Future is a nonpartisan event about near-Earth space infrastructure from now to 2035. Foundation for the Future is dedicated to the creation of a public-private partnership for space infrastructure development. To support this cause or to sponsor one of our events, please visit us at our website at www.f4f.space. That's with the number 4. And we are grateful for the support of our corporate and individual partners.